So last question in the packet. Tomorrow we will begin the part 2 packet. And again, it's all about reactions and anionic equations. The last one. Concentrated sulfuric acid, which is 18.4 molar, has a density of 1.85 grams per milliliter. After dilution with water to 5.2 molar, the solution now has a density of 1.83 grams per milliliter. Now, let me ask you something. This is an important question. What is density by definition? Mass over volume. What is mass by definition? Not the unit, by definition. It's the amount of matter that an object has. What is volume by definition? The amount of space. So density is the amount of matter packed within a certain amount of space. Would you agree? Now, so here's my question. The original concentration was 18.4. Let's think about this. What is the definition of concentration, or molarity? Mole per liter. Density is gram per liter. So the only difference is that we look at density as a mass unit, and we look at molarity as a what? Mole unit. So are they very similar? Can you go from grams to moles? And they're identical. So really, density and molarity are identical, other than the fact that we're looking at two different types of top things. But do they represent the same type of stuff? Because all we're doing is counting the matter that's involved with it, right? Where mass is the amount of matter and moles is the number of particles. Okay, so it's kind of the same concept. So my question here is, why did the density go down when we diluted it? Okay. All right, so let me ask you this. Did we add any more particles of the solute? No. Sulfuric acid. We didn't add any more hydrogen ions or sulfate ions. True? All we added was what? All we added was water. So we have the same number of particles in what? A different volume. When it says dilution, did we add volume or take away volume? We added more water. So it's the same number of particles in more space. So what does that allow the particles to do? Spread out. Well, what happens then to the density? It goes down. So logically, does that make sense? Put them in that box. Thank you. Okay. So logically, does it make sense why the density is different? Okay. All right. So it has a density of 1.38 grams per milliliter and can be used as an electrolyte. What does it mean as an electrolyte? It conducts current, okay? In a lead storage battery for automobiles, and that is true. If you guys go out to your car, and this is a genuine question, please don't yell or scream at me. I just want to know, how many of you could go to your car right now and pop your hood? If whatever vehicle you ever drive, could you pop the hood of the vehicle? Okay, that scares. I was scared for just a minute. So I want to make sure that you can pop the hood. All right, I just want to know if you could pop the hood. That's it. Can you at least get the hood up? Okay. All right. So, if you go out there and you pop the hood and you look at the batteries, there are sometimes corrosion builds up around your electrodes. And we're going to talk a lot about electrochemistry, what batteries are and how they work and all that good stuff. So you can clean them off, but what's actually happening is the corrosion of the sulfuric acid that happens around those batteries. Because there are actually little plastic plates that you can pop off of those batteries, and you can actually look down inside and see the sulfuric acid and the solution that's in it. Okay. Yeah, they're lead plates, and what happens is the current runs back and forth because of the electrons that are in there, okay? So, here's what we need. We need to calculate the volume of the concentrated acid required to prepare 1 liter of the 5.2 molar sulfuric acid. So, my question to you is, what's the question? Okay. Now, I like how you said that, Trevor. You said the volume of the stock. How do you know it's the stock? Because it says the concentrated solution. So you guys solve for V what? S. Solve for VS. Go ahead and solve for VS, sir. Okay. 5.2, yes, sir. I agree with you. I'm going to be honest with you. I don't know the proportionality difference between how much volume decreases the density by so much. I really don't know. And I think what it has to do with is how much water that you add to get it down that far. Because what we can do in a second is once we find this answer, we can figure out how much water we poured in to be able to dilute it to the 5.2. Does that make sense? And then once we figure that out, really what density is how much water can we put in between those particles to space them out far enough to change the density. I'm sure there is some ratio of how it works, and it may honestly depend upon the types of particles. I just don't know what that is. Okay, yes ma'am. Okay. You can't come in here and I don't send quizzes or tests. I mean, if you were to come right after school, it'll take 5 minutes. Just put it in that box. Mason, you had a question? Yeah. All right, so let's look at it. We should have established that we're using MSVS equals MDVD. And you guys said we're solving for the volume of the concentrated, which again stands for the stock. And if you want to write that up top, it may help you out. So we're solving for VS, which is MDVD over MS. Now, you've already told me that they give you the concentrated molarity. The concentration of the they give you the molarity of the concentrated acid. Okay. We know that if we've got a stock and we've got a dilute, I don't care what words it uses, which number must be the stock concentration. The higher one. Well, what's higher out of 18.4 and 5.2? 18.4. So we know that 18.4 must go on the bottom. Now, there's only one other molarity anywhere in this problem, right? And what is it? 5.2. And didn't it tell you that it was diluted to 5.2 molar? Yes. And what was the volume of that 5.2 molar solution? 1 liter. Why would you need that? And that's what I'm trying to get you guys to see and understand. This is going to happen a lot. In the stem of the question, they're going to give you data that you don't need for every single part. We may need it for the next one, but we don't need it for this one. You can't use everything they give you in every part of every problem. You've got to figure out what they're asking, what you have, and what you need. Yes, ma'am. Okay, sorry. I was just explaining why the densities changed. Because had I not, my fear would have been if I said the concentrated sulfuric acid has a density of 1.85 and then the diluted 5.2 has a density of 1.83. If I had just read that and skipped right over it, I'm scared that someone would have said, wait a minute, why did the density change? All you did was dilute it. I want to explain why the density changed. And I think that helped you kind of visualize what was going on in there. Now, what is the concentration, what is the volume of the concentrated stock solution that you needed? Say it again. 0.283 liters. If I handed you some 3 sig figs, 3 sig fig, and 3 sig figs. So now, hold that, no, I'm going somewhere else. If I handed you some glassware and I said measure that out, would that be a difficult thing or really easy? Physically, that would be difficult. So how could you restate this to make it really easy? Okay, so 283 milliliters of H2SO4. Now, if you wrote 0.283 liters and stopped, you are absolutely 100% correct and you are fine. But as we go throughout the year, you're going to hear this common theme. Write it in the format that's the easiest to physically complete and do. 0.283 liters is a challenging task, but 283 milliliters is much easier. So try. You don't have to. Try to give your unit and the one that if you had to do it, it's a lot easier. Instead of writing 493,281 grams, change it to kilograms, right? Does that make sense? Okay. All right, so let's look at part B. Calculate the volume. Stop right there. I know I need a liter or milliliter of the 0.52 molar. So actually, I want to pause on B for just a second. Let's go back to A, because I'm going to tell you, you're going to see it in just a second. And this is actually right above where we just were. So it should be the top left question. The top left question said explain or describe, correct? We don't want you to write it. I don't want you to write it down, but I want to verbalize it. I want to talk about it. If part B said explain what you would do, okay? First question is, how much of the stock concentration would you have to measure out? 283 milliliters. Would you agree? Go ahead. Do you want to say it? Ooh, boy. Look at you go. Okay. I'm just asking. We know we need at least 283 milliliters of stock concentrated 18.4 molar sulfuric acid, right? My question is, how big of a volumetric flask would you need to pour this in? 1 liter. Now, what Trevor said is of utmost importance. Why do we have to put water in first? We're not going to win. We're going to all. Okay, we want to all. No. We're not going to win. We want to all. So, my follow-up, yeah, we want to pour the fries in the grease, not the grease on the fries. Is another way to kind of think about it. Now, does it matter how much water you put in? No. If we have a 1 liter flask, this is an approximation. What percentage of the flask would the 283 milliliters take up? About a fourth. 25%. Do you agree? Because 250 is a fourth of 1,000. Does that make sense? 250 plus 250 plus 250 plus 250 makes up 1,000. So about 20, right above 25%. So if you filled up that 1 liter volumetric flask half full and then poured the 283 in, you're not at your 100%, right? Does it have more room to pour water in on the top? Visually, that's kind of what I want you guys to see. So again, I think y'all like drawing, like does drawing help visualize? Okay, so I've got this. So if this is an exactly 1,000 milliliters or a 1 liter, you guys told me that the 283 milliliters is approximately 25%. So if I filled this thing up exactly with 500 milliliters, what percent is that? Was somebody learn? That's exactly 50%. Well, if I poured in that strong acid and I took up another 25%, what percent left do you have to add water on top? 25. Did they change you? Yeah. Okay, she did leave you in here. Good. No. All right. So real quick, just want to make sure, since we filled it up halfway, we put our approximate 25% of our strong acid in, and how much would you have left to add water on top? About 25% left, right? So visibly, does that kind of make sense? So you could say in your explanation, like Trevor pointed out, we're going to all not win. We could fill it up about halfway with what kind of stuff? Distilled water, okay? Then we would pour in our 283 milliliters and then fill it up to the line on the with the meniscus on the line, right? We just want to make sure we covered that. Yes, sir. Okay. Dustin, you're such a dork. You really have to pay attention to your percentages, because what if you had to add 650 milliliters of your acid? Well, that's over halfway. So you would I'd fill it up a quarter of the way. approximately 25%. That would give you some. You really just kind of have to justify what your percentage would be. Go ahead. No, go ahead. I would say I would fill up the 1 liter volumetric flask about half full of the distilled water, then pour the volume of the acid in, then fill it up the rest of the way with water. Does that make sense? And the only reason we're putting water in first is to absorb the heat when we pour the acid into the water. That's the only reason. So acid to water. We're going to awe it, not whan. Okay, David. Okay, so that's a good question. So if I go back to this, if I fill it up halfway, that's 50%, right? That's 500 milliliters. Then if I add my 283, that's about 28%. Is that my full 1 liter of new acid solution? No, that's why I have to fill it the rest of the way. Does that make sense? So what I would have to do is come in and then fill it with the rest of the 25%, and that gives me my 1 liter. Okay? Any other questions on this? All right, so let's go back to B. So B says calculate the volume of 5.2 molar sulfuric acid that can be completely neutralized with 10.5 grams of sodium bicarbonate. No. Pause. Do me a favor. Out beside sodium bicarbonate, please write baking soda. Here's what you're dealing with. You're dealing with your salt. Acid-base reactions always produce a salt and a water. The salt has neutralization powers as well, because what's going to happen is you're going to take that anion and you're going to eat up that acid. You'll see in a second. You with me? Just stay with me, sir. Very good. So here's the problem. What he just said is a very important question. We're trying to find a volume of an acid that can be completely what? Neutralized. And I told you, when you see neutralized, that is telling you acid base. But here's the deal. When it says 10.5 grams of sodium bicarbonate, that gives you that formula. A bell should be alarming in your head. Sodium bicarbonate. Is that a base? No. This is your salt. So see if you can set up a balanced equation. Actually, you know what? I'm telling you backwards. Completely ignore what I just said. Hey, stay with me. I'm being an idiot. Please ignore me. So write this part down that I have right here. We're going to write a balanced equation. I'm being an idiot. I'm going to pour some baking soda on some sulfuric acid. Would you agree that baking soda is a part of the reaction? So is it a reactant? Duh. I'm sorry. I apologize. So it's NaHCO3. Now this looks a little prettier. Now, that's a great question. Yep. What you're going to get is you're going to get sodium sulfate. This is going to be a double replacement reaction. So this is, give me a second. Just watch me for just a second, okay? I'm not going to change anything. I just need to show you something. Do you agree that we have a double replacement reaction? What I'm going to do is I'm going to split this. We have 2 hydrogen ions plus a sulfate ion, right? Don't write any of this down. Just watch me do it. We also have a sodium ion plus the hydrogen carbonate. Nope, that's not right. Plus that. This is where I need you to just see this part from. Okay? Who is Na going to hook up with? Those two things, right? So now let's write that as one of our products. Na2SO4. Now, here's where we have to really pay attention. Do you agree that the H is going to hook up with HCO3 negative? Now, whenever you write a new compound, what do? Check your charges. So I need an H and I need an HCO3 negative. Do you agree or disagree? Hold on. Stay with me. Why does this 2 not matter over there? That 2 is for this thing, not that thing. Could you write it like this? But how ridiculous does that look? That looks stupid. But is it true that that's technically your ion-to-ion connection? Yes. How would you really write it? H2CO3. So write that down as your other product. I wanted to show you this because I think visually you needed to see it broken in half. Hold on. Let me do it one at a time. Why doesn't this 2 matter? Do you agree that that 2 belonged to the sulfuric acid? When we write new compounds, you got to completely ignore what's over here because it's brand new, right? You got to follow these rules. I've got a hydrogen hooking up with a hydrogen carbonate. Okay? 1 plus, 1 minus. This is the weird way to write it. But that's technically your cation and your anion connection. So it's not really a pretty way to write it, is it? That's why we just combine the H's and write it like that. Okay? Next question. It is, but why is it not 2 negative? Oh, excuse me. Yeah. You're right. But no, this technically isn't true. The reason that you're saying carbonate brings this 2 down, that's really not the case in this one because this is what it really is. Not really. It's really because it's not carbonate. It's hydrogen carbonate, which is different. Trevor? Yes, sir. Because it's hydrogen carbonate as an entity. It's a polyatomic. You can't lose this H right here because it's a part of the polyatomic. Jamil? Wow, thank you. Sorry. Was a chance. Will you grab those from her, please? Somebody else had a question. Over here. Yes, ma'am. We're going to. We just haven't got that far yet. All right. So any questions on how and why the reactants are what they are and the products what they are? We all good on from that perspective. Okay? All right, so let's erase this. Dustin, are you tapping your feet? You sure? Okay. Whoever's tapping their feet is like nails on a chalkboard. Now let's go back and balance it. So I've got 3 H's, 2 H's, 1 S, 1 S. How many O's on the left? 7. How many O's on the right? 7. Did I miss an H somewhere? All right, so we need to balance this thing. Oh, here it is. 2 and 2. Now it's balanced. The reason I know that is because look right here in black. In black I had 1 Na, right? In red, how many Nas do I have there? 2. Well, that took care of that for me. Now, it took care of the carbonate, and it took care of the carbonate. Now, let's recount them. I've got 2 plus 2 H's is 4. On the other side, 2 times 2 is 4. All right, S, 1S, 1S. Oxygens. Now I've got 4 plus 6 is 10. On the other side, 4 plus 6 is 10. Carbon, 2 and 2, 2 and 2, and sodium is 2 and 2. So everything balances. Yes, ma'am, it applies to every single element in the group. Dustin? Yes. And the carbonates, because they're on both sides. They have to match on both sides. All right, so now let's actually get into the problem. Help me out, how many grams of sodium bicarbonate were we working with? 10 and a half. They gave you something else. We're searching for the volume of what? Our 5.20 molar, and we're searching for the volume of what stuff? Sulfuric acid. So I'm looking for the volume of this thing. Agree or disagree? Agree. All right. All right. So why do you need a balanced equation? Are you going from one compound to a different compound? So my question to you is, we've got to go from the baking soda to the sulfuric acid. The only way to go from one thing to the next is mole to mole. Okay, so let's set up our stoich. We've got to stoich this out. Let's kind of talk through it as we go. We know we have to do stoichiometry, right? We know at least we got to get to mole to mole. That's a great question. Dustin, you got that yet? Now, please excuse my French, but I'm going to label that as BS. Do you know what BS stands for? Baking soda. This is baking soda. I don't know what trigger warning means. I don't know what that means. Okay. Now, we know that this is true. I don't like grams. If you got to find grams, it's a pain in your... Now, I know that this is absolutely without a doubt true, correct? Because I don't want moles of baking soda, so I got to get rid of it. Now, I know eventually I got to get to sulfuric acid somehow, some way. True or false? True. So because of that fact, I know that I have to get from baking soda to sulfuric acid through what step? Mole to mole. So I'm going to write SA for sulfuric acid. Again, on the real day, please write the real formulas. We're just going to brief shorthand it for today. Yes, sir. Okay. Now, my question to you is, what is your mole to mole ratio top to bottom? 1 to 2. Now, this is where I'm going to make a very important statement to you guys. What am I trying to get to? Trying to get to volume. Hold on. You haven't answered my question. My question is, what am I trying to get to? Trying to get to volume. Now, Elizabeth, you gave a little girly shrill, so I have a feeling you've picked up on what's going to happen here. Before you give me that, I'm going to ask this question. I know that I can't have moles of SA. At a minimum, what do I do here? I got to get rid of moles of SA. Now, here's my question. Elizabeth, what was your shrill about? Interesting. Continue. Interesting. Fill me in. Fill me in. So what can I have up here? Can I put liters of SA right here? Now, hold on. Stay with me. Now, this looks a little funny. The reason it looks funny is because it's what over what? Liters over moles. But let me ask you something. I don't care that molarity is moles per liters in terms of the M. But when you say it, molarity is so many moles per what? 1 liter. Is it still a ratio? Is it still a relationship? Yes. So what you know is that for every 1 liter of sulfuric acid, there are how many moles in it? It is. What does molarity stand for? Mole over liter. But this is just the opposite. It's still a relationship. 5.2 moles in every what? 1 liter. So this is still my molarity. And the reason it's making your brain sizzle is because it's written as liters over mole. But isn't it the exact same thing? For every 1 liter, how many moles are in it? 5.2. There are 5.2 moles in every 1 liter. It's just a ratio. It's just a relationship. So you can use it just like this. So my question to you is, what were we looking for? What was the question? Volume of sulfuric acid. What are we in our stoichiometry? Volume of stoichiometry. Volume of sulfuric acid. Does everyone understand that last step? Let me ask you this. Here's the part that throws everyone off every year. Had I asked you to find the grams of sulfuric acid, your brain wouldn't be sizzling, would it? Because you've been doing moles to grams forever. But as soon as I throw that liter in, everything just comes out your back end. Okay? You've got to understand that what is molar's mass as unit? What is molar mass? Molar mass is gram per mole. Are you with me? So, here's the crazy part of this. You have always said, if I've got 10 grams of X, what happens here? You don't freak out when you see this, do you? Because if X has a mass of 5, you've always done this. Oh. So you're telling me now, instead of me having, if I've got 10 moles of X, that why can't I just do mole per liter? It's the same thing, it's just upside down. It doesn't look right, but you've been doing this the whole time. You just didn't realize you were doing it. This right here is the same thing as the molar mass, and you've never bucked on it before. Why buck now? How am I betraying you? I've never told you that it was any different. Say it again, Nicole. Does this make sense? You've just never viewed it from that perspective. Well, because we harp on molarity, mole per liter, mole per liter, mole per liter. Well, when I say liter per mole, whoa, hold your horses. That's not right. Yes, it is. It's the same thing. It's just looking at it from the other side. No. I'm not trying to look at it in that perspective. I'm trying to figure out what is my relationship. My relationship is 5 grams in 1 mole. In my molarity, it's 5.2 moles in 1 liter. It's still the same. You're just looking at it from the upside down position. Because I have 1 liter. That's the part where you can't have 2 liters in a molarity because it's something per 1 liter. Okay? So, let's go back and someone give me my answer. You said milliliters. I like it better. What? Now, Mary Beth, I heard you say 0.012. Again, 0.012 would be an acceptable answer. But again, it would be a very difficult thing for you to physically do. I can hand you a 50 milliliter graduated cylinder, 25 milliliter graduated cylinder, and that's easy. Yes, sir. Absolutely, you could. I just wrote essay just to be lazy. Any questions? Are we good? Okay. What part can I re-explain to make it make more sense? Yeah. Here. Okay. All right, so, and I agree with you. So let's see what he was saying. So if and I really hate to do all this, erase this beautiful work, but it is what it is. Shut up. So now that you've given me your moles, give me what was my number of moles? 10.5 divided by those two things. So now if you want to do it like this, that's perfectly acceptable. But guess what you fools need to realize? I'm trying to sorry, that was rude. I apologize. That's fine. I sincerely apologize. You are all wonderful, well-rounded individuals. Tell me mathematically what you're doing in that black triangle. You're dividing your number of moles by your what? Look at what you guys just did in that stoichiometry. You did the exact same thing. Exactly. No, I'm telling you guys. Hang on one second. This is it. Put them in that box for me, please. This orange, what I just added back was what you guys wrote down a minute ago. So you're telling me that instead of just doing one more tiny step, you're going to hit equals, write down a number, plug it in a triangle, then divide, then hit equals again? No, don't. No, it doesn't. If you... I really, I'm kind of getting frustrated, to be honest with you. It is funny, but at some point, you have to listen to efficiency. You have to understand that I'm teaching you guys the fastest, easiest, simplest way. And if you continue to just push back and you continue to say, I'm going to do it the hard way, it's going to be a really long year. You have to commit to learning how to do things the most efficient and fundamentally the simplest way. What you're doing is you're adding steps and you're adding opportunities to mess up your work. If you'll commit to 3 steps, you're done. Why try to make it more complicated than it has to be? If I ask you to go to the office, you're not going to go to the gym and then up there. That's stupid. Don't do that. Go straight there. This is a straight, direct line to where you're trying to get to. Don't make it harder than it has to be. Commit to understanding that fractions are ratios in relationships. Just like gram per mole is a relationship, so is mole per liter. So is gram per cubic centimeter. It's all a relationship. It's all a ratio, and it can be plugged into this. Tristan. Okay. But why would you do that when you can do exactly what I have written and it saves you time? Okay, but why hit equals and you don't have to? No, they're not. And that's the part that you guys have got to understand. I have to teach you the basic stuff before you can understand the complicated stuff. This isn't complicated. It's just you forgetting how you've always done it and doing it a little bit different to get an easier way to do it. This is easier. I'm teaching you the easiest way to do this, and you're yelling at me, telling me, no, we want to do the hard way. Why would you do that? I can't. All right, so we're going to move on. So what I need you guys to do, I'm going to do something in just a minute, but I want you guys to pull out, it's this sheet, okay? I wasn't born yesterday. It's the molarity dilution practice. If you'll flip it over, because you did none of those problems on the back, okay? It was 1 through 5 on the front, 6 through 10 on the back. What I want you to do for the rest of the time that I'm going to give you guys to work is I want to see by yourself. Do not work with anyone else. If you've got a question, I'll come to you. See if you can figure out how to do these problems. I tell you what, do me a favor. Number 6 says describe. I'm going to give you some freebies here. Don't describe number 6. Just do the straight math. Okay? We'll talk about describe later, but I want to see if you guys can do this. So take the time to work 1 through 10. And I'm going to tell you, when you get to the bottom, it's going to be challenging. You have to pay attention to what's going on. And put a little star beside number 9. If you have your notes out, you should have left them out if you can get back to them. Beside number 9, please write total, and that should give you a clue. Okay, total, because you have to read the question. We've worked an example problem just like number 9. You may have to go back and look at it, sir. Yeah, just do the math. Don't describe. Just the math.